So this is going to be a really interesting juxtaposition from the previous talk, because I'm actually one of those people that comes from an engineering background and ended up in healthcare. So does that make me the hammer or does it make me the nail? But either way, there's some interesting similarities between these two talks, and I think we come from slightly different perspectives. But it will become clearer as we move through the talk. I'm not going to talk too much about foreign institutes or any of those kind of projects. I've taken the license granted to me of standing in at short notice to muse on various things around data and AI, so hopefully we'll get somewhere. What's all the fuss about AI? Why do people care at the moment? Because it's not a particularly new thing. Well, there are a number of different things that have happened. One, computing power has become incredibly cheap, actually driven largely by the gaming industry, creating things called GPUs, which give you massive amounts of computational power in a small form factor in very high density. The other thing is methodological development. So over the course of the past 10 years, there have been some breakthroughs around machine learning, neural networks, that means we can scale these things up like we've never been able to scale them before, which gives them incredible power. And then the crucial thing, the third thing, is data. We have enormous volumes of data and all kinds of varieties, all kinds of speed at which it arrives, and as Paul mentioned, veracity of it is extremely important as well. But it's the confluence of these three things that is now starting to really change healthcare and will do over the course of the next few decades. You probably hear these terms all the time as well. Big data, machine learning, deep learning, data science, artificial intelligence. They're kind of the same thing, really, more or less. This is the popularity of these as search terms in Google over the last 5 years. And you'll see big data was really, really popular right at the start. Machine learning, deep learning, data science, artificial intelligence, less so. But now machine learning has outranked big data. And so actually, we're all about machine learning now. I just wanted to make a comment as well about what actually is big data. So if you are a physicist, you're working on big science projects, things like the Square Kilometre Array, Large Hadron Collider, the Large Synoptic Sky Survey Telescope. These produce really, really big data in terms of the size of the records and the speed at which those records are generated. When we move down into the biological domain or healthcare domain, we start to look at omics, which is relatively large compared to imaging data, which is smaller still. And then we get down to the kinds of data that I normally deal with and people in this room deal with: health record data, clinical trial data. So actually in the terms of what's big data, it's actually pretty small data. But often when we use the term big data, we're talking about how have we linked that data to sources of data it wasn't previously linked to. There is going to be a change as well in healthcare. So Martin mentioned it, IoT, wearables. This will produce large amounts of data. And as Rory said, the wearing of the accelerometers in UK Biobank, that's produced a large amount of data where actually you've got very small records, but you get them produced very quickly and high volume. So that's where we are really in terms of the space of big data. I mentioned as well that artificial intelligence is not a new thing. And this is actually the history of the perceptron, which turned into the deep learning neural network that drives all the innovations today. And these things have been around since 1940s. They have had a number of crises over the years. So at the end of the 60s, we had the XOR problem, when it was demonstrated they couldn't solve the logical formation of the XOR. But then we've gone through the dark age, the AI winter, mid-80s, re-emerged through better learning teaching techniques. And then we've ended up where we are today, which is really the deep learning neural network, which gives us a much greater power. So I also wanted to distinguish between machine learning and generalized artificial intelligence. So if you listen to the late Stephen Hawking or indeed Elon Musk, they get very exercised about generalized super artificial intelligence that outstrips human performance. This is not what we're talking about. We're talking really about machine learning that actually is very specialized, is very narrow, but is very good at those particular tasks. Paul touched on this as well, actually. What's the difference between machine learning and statistics? Well, this is a handy explainer for you. These two things have kind of been developed independently by different academic communities, but actually they were doing the same thing, but using different languages and publishing in different places, almost developing in parallel. But there's some interesting things about the difference between these communities. For example, a large grant in machine learning is about $1 million. A large grant in statistics is about 50. So if you want to improve your research career, rebrand yourself of that if you are one of those. Also, you get to go to nicer places as well. So actually these two things are very, very similar. An example of artificial intelligence in healthcare is the MySyn system, Edward Shortliff in 1974, which was an expert system for actually bacterial infections and actually advising on diagnostics and treatments. It's a different kind of artificial intelligence system than the neural networks, in that it's just a sequence of rules that says if this, then this. But it was an early example of a success in artificial intelligence in medicine, and it was able to explain why and how the decisions that it had made. And then we get up to this, which Paul has already talked about, which is Esteva's paper on how you actually diagnose skin cancer from images, and we use the full power of deep learning neural networks, and it outperforms humans. So that's bringing us right up to date. My own research, it focuses around a lot of what happens when we put these algorithms, these machines, into the healthcare process. So conventionally, very simplistically, this is how we deliver healthcare today: direct interaction between the patient and the healthcare professional. Then we introduce the algorithm into the picture, the machine, a bit of intelligence, that possibly automated. And this changes the interaction we have. So healthcare professionals start using this for decision support, early warning, intervention. And then it gets really interesting when the patient themselves starts interacting with the algorithm: decision support, self-management, self-report adherence. So just wanted to explore some of the observations and some of the experiences I've had around developing these things and how they fit into healthcare, and actually some of the implications for artificial intelligence in healthcare as well. And I suppose the thing is, these are the tests that we apply to a medicine, a medical device, and actually these are the tests we also need to apply to algorithms when we use them in healthcare as well. Efficient, effective, safe, acceptable, equitable. So here's an example of something that I've been working on in collaboration with psychiatrist colleagues of mine. So this started as a mobile phone app for people with schizophrenia. And we first started working on this around 2010. Actually, I had the idea before that. It was around about 2009. And it's an app that enables you to self-monitor for schizophrenia. And we started by taking the clinical gold standard rating scale for schizophrenia, positive and negative symptom scale, and we translated that into a mobile phone app, a smartphone app, that prompts you and asks you questions at regular intervals through the day, and actually correlated that back to the clinician gold standard. So that was through some MRC funding around about 2012. We then extended that project to try and integrate it actually into the healthcare services, so that actually the data collected from this app It was actually sent to a server, and we were actually able to run an algorithm on top of that server, looking at that data, trying to identify relapse signatures for individuals. And once you're able to do that, you can then alert the care team, and the care team can go and intervene. So this is really good, because if you can identify people at risk of relapse and schizophrenia and go and intervene, you generally come out with a better outcome, which is much better for the patient, but it's also much better as well for the system, because it reduces hospitalisation, therefore saving cost. What's interesting about this, and the first point of learning, is we wrote the first grant around about, as I said, 2009, and we included these things in it because that was the state of the art at the time. I'm sure there are a number of people in the room who's probably used one of these throughout the course of their career. So everybody's favourite Palm Pilot tungsten. By the time we were awarded the grant and got started, these things completely obsolete, discontinued. Apple had put the smartphone out, so what were you going to do? We could try and get them second-hand from eBay, or we could actually just change with the technology and move with the times. And this is the first point of learning, I think, is that the pace of evidence collection that we go through, we write a grant, we hope to get some funding, we start with the study, the randomised controlled trial, whatever it is, but these things, the technology moves much faster than we can collect the evidence. So what do we do about that? Paul also had this one as well, so adaptive systems. So actually, a lot of the good algorithms, the good systems, learn from the data that is produced and their experience of their performance. Satellite navigation is a good one of these. But actually, how do we ensure that adaptive systems such as this actually continue to be effective, continue to be safe? And as Paul alluded to, the regulators do not have a good answer for this problem. And yet, industry is going along, is developing these systems, they're starting to get good results, but actually we're at risk of deploying these things that we cannot tell how they're going to perform under future circumstances. That's the next one. Actually, there's an example here of one we developed ourselves. So again, this is research from psychiatry, schizophrenia, which is actually using raw GPS data collected from somebody's phone to actually try to infer social function. So where the places you go to, we can identify from those GPS data where you went to, and then we can try to infer the activities you all performed. Did you visit a friend? Did you go to the swimming pool? Did you take physical activity? And this system as well tries to learn from the data that's been produced as it goes along. So again, an adaptive system that tries to improve itself over time. Then we get into scenarios such as this. So many of you will probably have seen the recent troubling case of the Uber self-driving car that was self-driving that killed somebody, right? So it's an autonomous system. It is allowed to take actions, make decisions, has a performance level. But the question has to be, I think, is what is the acceptable error rate for this kind of system? We as humans, we also make mistakes all the time. Should these systems have the same kind of error rate that we do? Should they outperform us? Again, nobody has a good answer for this yet. Another one. So you'll also probably have heard of this one as well. Again, it's a DeepMind example, Google DeepMind. This is neural networks beating the world Go champion. Right? Go's an interesting one. Chess fell sometimes, I think it was around about the 2000s, through a brute force attack. So basically just a very large computer calculating through the entire search space and moves what was the best move. Chess is okay because it's on an 8x8 board. Go, much more complicated, combinatorial explosion, you can't do a brute force attack. However, what you can do is you can develop a reinforcement learning system that plays itself all the time and actually learns how to beat itself. And this proves to be very effective. When actually Lee Sedol was beaten by the DeepMind solution. The interesting thing about this is actually when you looked at it, it was performing some moves that even the best experts wouldn't have thought you would play. So it was almost like it was playing on intuition. It had learned intuition about the game of Go. The point with this is actually, you think back to the Meissen system I showed you with some if-then rules, you can work back through that and understand how it's reached a particular conclusion. With something like this, it is a black box. You cannot say or interpret it, its function, its operation. So the question then becomes, is it acceptable for us to use these black boxes in the provision of healthcare and making decisions? So that's another one we don't really have a good answer for yet. And then another one. So the key to all of this is actually data. So, and there have been a number of different efforts over this. Let's start with care.data, which many people in this room will be familiar with, which was a noble aim to bring together all the electronic health records of the population of the UK, and yet it failed. And the reasons why it failed were really because the public didn't trust it. It wasn't clear whose interest this was being done in. It wasn't clear that there was any kind of notion of reciprocity. So my data is going in there, but what do I get back? And this is a real problem around public attitudes to using data. And it's even been compounded even further over the course of the last week or two, where actually these companies, can they be trusted with our data? And this, again, is an ongoing discussion, an ongoing debate, but actually the future of AI hinges on the use of data, and the future of AI in healthcare especially so. So how do we trust these companies? And then I suppose another one that I to go through is, so you have a number of companies. I've got three here. I've got DeepMind, I've got Microsoft, I've got IBM. But there were a lot more companies. I'm not just picking on these three. But I suppose the question here is data is the key to AI. AI in healthcare is predicted to be a multi-billion market. How do we ensure that the value that exists inside this data, and think of NHS data, we all potentially own, how do we ensure that we create business models and the correct partnerships with these companies to ensure that the value trapped in that data continues to accrue to us as a nation and to the people of the UK? And this is actually quite opposite, because this has been raised. So, for example, Lord O'Shaughnessy very recently was talking about the UK's data as a sovereign asset. So actually, we need to generate as much value from this as we can. Lord Mitchell as well. How can we protect NHS data from big tech? And these questions, again, have not been answered. But I suppose that the point here is technology, industry is moving ahead with this stuff, but I think there are some fundamental things that we need to understand and work out where our position is, especially around NHS data, to ensure we maximise the value for us as a nation. So, just 6 things I think that I really wanted to provoke you with. Pace of technology development far outstrips the pace of evidence collection. How do we deal with that? How can we ensure adaptive systems are safe and maintain efficacy? Who's responsible when mistakes are made? How much autonomy should we give machines? What's the acceptable error rate? And this is actually further compounded when you look to a future where you have chains of algorithms all linked together, all making a decision. How acceptable are black boxes in this process? Can we rely on them? Should we rely on them? We can't inspect deep learning systems. And who do we trust? Who do we trust with a particular piece of AI? If it's a black box, who made it? Why did they make it? Does it matter? Again, another open question. And then finally, we need to ensure that we do all benefit from the data asset that we have in the UK. And actually, relationships, business models, ensure we recoup the value in the long term, not just the short term. And I'm finished there. Thank you.